传统的高频随机振动系统呢，其实20-30年来都没变过。无论是您这个振动看居值的一致性，或者是说响应值测试的有效性，尤其我们的系统可以无缝的导入你原有的系统，然后在测试性能上面，或者是节能方面、扩充产能等等的，都有很大的优势。
So for GIS label, because we separate the table to four quadrants, right?
Yep.
So is there any spec for this?
We don't have a published tolerance spec on this is out of spec or this is in spec. We've been working on one. I've compiled a lot of data of all the tables that we made in the current design, so I know where they are and the difference between them. So it's something that we'll probably be doing soon. Is having an actual spec as far as in tolerance or out of tolerance. The challenge is dealing with vibration. Is that given when you find a difference, it's not like a 10% or 20% difference. Everything is exponential. So on one table at one certain frequency is slightly stronger than another table, while in vibration, slightly stronger would be 100 times more powerful at that frequency than another table. So it's difficult to come up with just a clear-cut tolerance of here's the average PSD, and anything within 10% either way is okay, because most tables wouldn't pass that, just because of the nature of vibration. Whereas, like I was saying, if you excite one frequency, it'll jump to 100 or 1,000 times the power of other frequencies. So it's kind of difficult to come up with a clear-cut, I guess.
So meaning currently it's not, but
we
you're
don't
working
have
on
a
it.
spec currently as far as what's in spec and what's out of spec. GRMS-wise, it's a bit easier because that's just adding up all of the power that it sees, and of course that is something that you can say it must be within 15% or so.
But you don't have that spec also, even it's in GRMS, right?
Well, in GRMS we do as far as what the max G is on tables.
Oh, I mean the uniformity-wise.
Uniformity-wise, there's no spec on that on the Typhoon. Now on the Q-Fusion tables, I'm developing that since there's been a lot more focus on uniformity with Q-Fusion than on Typhoon because it's actually designed for HASS, and it's designed to put a lot of products in there at once.
So when we define the performance of table, like we perform the table matching this year, and we perform it again next year.
Yep.
So because we need a very clear number or clear way to know, okay, this table is bad, or there is something wrong. So
the way I recommend that is comparing the data to what was originally done on that table at the factory. But you're right. It'd be very nice to have just a global spec for all of the tables.
I think you have one, like the degradation when you run the max throttle. And
we do have a degradation spec.
Yeah.
That's a rebuild procedure for XLF2s, where if the max G goes down 20% from what it was new, it's time to rebuild it.
So is it applied?
Yeah.
So is it applied to any table that we can use the 20% degradation as a spec to?
That was specifically developed for XLF2 because I tested specifically for that. On the tables for Q-Fusion, just inherently in the design, I don't foresee them wearing out in that same method. I think it'll be either they're okay or they're not okay. And I'm going to have to work with you guys on longer term testing to help you guys out.
There's nothing to degrade, it's a solid piece.
Exactly, that's it. It's the table it doesn't have the sandwich as what you find in an XLF2. And so that's why I say that it's probably going to be okay or not okay. Now as far as long-term testing, I've done the longest term test on the Quake table that's in the Q-Fusion was longer than the long-term test on the XLF2, and there was no measurable degradation at all. So that should give you a good indicator that it's just going to run.
That was hundreds, thousands of hours? Thousands of hours.
Yeah.
okay, since table mapping is for check out the table performance, right? So that's the uniformity of table.
Now for Q-Fusion, as you know on Typhoon, the focus is quadrants on the table. Q-Fusion, as it was designed, was each table is designed for one fixture. And so instead it didn't make sense to measure the corners of the Q-Fusion tables because it was made for just one picture. So that's why I developed a new method to test where we have a square plate and you just move the plate across the table as if it's in different slots, like a fixture. So that, I'll be measuring that next week. So
the purpose of the table mapping on Q-Fusion table, what is that?
the purpose of mapping the Q-Fusion table is the same type of idea. So we can compare each table to table, and then also uniformly from slot to slot, which gives you an idea of designing a fixture of what you have to overcome.
So the square plate you developed is somehow simulate how the power supply was located
Oh yeah, somewhat.
on the picture, right? Okay, so
It's basically a type of structure that you're bolting to the table that will add some mass and some stiffness with an accelerometer on there.
So for single table, that 5 locations also measures the uniformity of one table? Or?
Yep.
Okay.
And
So
then
that
you can compare the results from one table to another table. So that's how
location to location.
Yeah, so we'll make sure that the tables are uniform. Now that was one of the major design efforts in Q-Fusion, was simplify everything, but to just make it easier to be uniform.
So can I make a comment that on Typhoon, the table mapping is not designed for uniformity test. It's designed for table characterization.
Yeah, the Typhoons, XL2, and XLF were designed initially for halt testing, which explains the design that they are. So whereas the Q-Fusion was designed from the start is, okay, we're designing this to have a lot of small electronic components on there at the same time for HASS and HASS. So the whole goal was, I want the same energy in this slot as this slot in that slot.
Okay, talking about the same energy, you were talking about GRMS level, or even to look at PSD.
Yeah, so in the development of the table, I had several different fixtures, and so every time I did a test, an iteration of the table and the fixtures that I was working with, I was always looking at GRMS and spec in each slot.
So you're saying that the 15% consistency requirement is also including the spectrum factors in it?
The 15% spec, that's the 15 plus or minus 15% GRMS level slot requirement from HP.
That's only for GRMS.
It's only applied to GRMS, but I found through the testing that if you can get within the GRMS spec slot to slot, typically your PSD is going to be very similar.
But that's the PSD on the table itself, not on the
No, I'm talking on the product slot to slot.
So where do you put the product? It's on the case or is it inside?
On the board.
On the board itself.
Yeah.
Oh, great. Good news.
Yeah, I can show you the test piece I have.
Because there is a controversy for vibration uniformity.
Yeah.
Because like in the field, users may get easy to put accelerators on our table.
Yeah.
Maybe they take 25 samples, just in case you set up for 10 kg, and they will get the result from 6 to 12.
GRMS across the table?
Yeah, GRMS. So in this 25 sample. So they are curious and argue why so different.
Let me explain that. It's a good question. So as you know, on a typical PSD, frequency, power, as I was explaining earlier, if you look at the PSD with the linear axes, most of the energy will be fairly low, and then you'll pick up some resonance where you have a big spike, and then you'll have some more power, and then you pick up another big resonance, and then you'll have some more power and another big resonance. And in a perfect world, we would get this to be a straight line. But the reality is it's really difficult to do that. And on the Q-Fusion tables, I did take another step towards that by spreading out the energy. But it's almost impossible to get around this somewhat. So you can think of it as most of the energy is in a straight line. But there's certain resonances that come through at 100, 1,000 times the power of the rest. And it's just inherent in vibration that it happens that way, in just natural frequencies. So what's happening when they're going across the table and they'll see 6 Gs here and 20 Gs there, is when they see 6 Gs, will be that. And then when they get to a point where they're picking up a resonance that wasn't there on the last point, that's when it'll jump up to say 25 Gs. It's really, if you compare the spectrums from a spot that was low G and high G, you would probably notice several resonances picking up on the high G spots that aren't in the low G spots. So that's where it's coming from. It's not that everything on the whole graph is twice as powerful. It would be, most of the graph is the same. There'll be several resonances that come through on the high G versus the low G.
So what are the factors that different locations picks up different resonance? As I said, it's because of the actuator locations?
It's because you have a table that, this is just a kind of theoretical table here, an example. Say if you have a hammer that mounts at each of those positions, and then you have some webbing that goes between them that's maybe shaped like this, and you have some more webbing that does this. All of that stuff responds differently in the vibration. And also, as you go through, if you just watch one spot versus time, that one spot will change, just inherent due to its random vibration coming from the hammers. And so as you have, like you took a tub of water, and you hit the surface, you see a lot of waves go out. Well, if you hit this surface, and then hit that one, and then hit over here, and then hit over there, you'd have waves going all over the place, and then when one wave hit another wave, it would create something different. And you have the same type of thing going on with the table. And that's why you can get different power levels at different spots. Yeah, if you have, some wave tends to always come out from this hammer, and it tends to always get hit from a different one from this angle, over a rib in the table, it could possibly make a spot that tends to have, more resonances than another spot.
Isn't it true the table's not solid? It's like the surface of the water or a piece of aluminum foil or something.
Yeah, the weight action. Exactly. Yeah. If you do look at the table very closely, it's not moving as one piece. It's flexing and waving like the surface of the water that you hit.
So can I explain this way, the shock wave energy creeping as the waves interact with each other, so that the energy in one location will differ from time to another time, and also location to locations will be different because of the actuators' allocations and how they interact with each other on the table itself.
Yeah, it would be kind of like on that water theory. If you always hit the same two spots, and there was some weird shape to whatever the contained water, the waves would always bounce off. There'd be several spots that would just tend to be a little bit more powerful than others. Now, I did try to reduce that effect on Q-Fusion. That was one of the things I took a step towards, was trying to reduce that, which I went through 5 generations of table design for this before we released it. And it did reduce some of that difference, but it's always going to be there. When you do bolt the fixture on, it does tend to even things out, because you're bolting more mass on there, and something that's stiff, and it tends to average out some of those.
So the air actuator technology, so-called as repetitive shock technology, is inherent to have this characteristic, right?
Yeah. Okay. Yeah. All vibration tables are going to do this, whether it's air or electrically driven. The only way to get around it entirely would be really a completely random vibration, which would be if the hammer itself was moving to random locations, and mechanically that's not very reasonable.
So only it creates a shock wave. I mean, if the energy source is shock wave, then it's going to happen this way.
Yeah. Okay. Especially if the shock is always coming from the same spots.
But whereas like the ED shakers, they're using the moving of the table itself to create energy. So that kind of
the difference there is that the ED shakers, the table itself is rigid, and everything's moving in unison.
Yeah.
In one axis. Yeah, in one axis. And it's all at a frequency determined by the shaker. The difference is in random shock, the table itself is flexing like the surface of the water. That's the difference.
When we talk about uniformity on UUT,
Yeah.
like we put a radar on PCB board, because like Dell, they have spec on it between UUT and UUT. So because they were not able to get uniformity from the table surface, how can we make sure uniformity on those PCB boards?
It is a challenge, and it is difficult. But when you tend to put a fixture on a table, say you had a hot spot that was 20 Gs there, but only 6 Gs there. Oops. When you bolt a fixture over that, it does average them out somewhat. But on the fixture design, and I spent a lot of time testing this for Q-Fusion, is you do have to really tune everything to work together, and that's why the fixture tuning is so crucial. Because it's really impossible to get the table to have exactly the same GRMS and same spectrum at every point on the table. And even if you did, as soon as you put a fixture on, it would not be like that anymore because the fixture changes it. So, but the fixture does tend to average out spots like this. So when you put it on, instead of maybe 6 and 20, they would be much closer, but you still do have to tune each fixture. And that is wise because, I mean, it's just impossible to get the table to do exactly the same thing everywhere. And, you know, even if it did, just you put the fixture on, that would change it and introduce differences that you then have to tune back out anyway.
The weights of the loading and the location of the loading will affect the responses
Yes.
on the UT. So I did a lot of tests to realize that.
Yeah, and that's why we've been going to things like adjustable fixtures where you can adjust the clamping load. And, you know, we did a lot of testing here trying to find out what else is an effective tuning tool besides just clamping force. Stiffness of the mount, instead of just nylon, we have some that are nylon and aluminum. And then we also did testing with the clamp force of the clamp that pushes front to back, not just the top down. We did testing on, you know, how tight the tolerance is on the width of the nylon pieces that the part slides into. So yeah, we've been working on it quite a bit just to make sure that if we make it as easy as we can for the customer and you guys to develop a fixture as easy as possible.
Can I say that anything within the energy transmission path and will alter the BSD shape will
Exactly.
be the factors,
Yeah.
and that is a lot.
Yeah, it's kind of a rule of thumb with vibration. If you're getting resonance somewhere that you don't want, all you have to do is change something.
Or put some.
Yeah, so if you get a vibration that's exactly how you want it,
Yeah.
then you add a fixture to it. Well, you just change the whole thing. So
Yeah.
it's always an iterative tuning process. We've been trying to reduce the iterations.
And I think both of us understand that, but it is hard to explain to the customer who
It is, yeah.
is not exposed to this RS technology for too long, or he doesn't have just spend time to understand the technology. So I'm not sure John is capable of delivering this information to our customers right now.
Yes, just because also they think to tune the uniformity on PCB board is a challenge. So they will feedback information to me, like can provide a table uniformity, and that will get very easy to perform the
Yeah.
test.
So that is one major requirement of Q-Fusion when we were developing it, was to make it easier than it currently is in the Typhoon. And that was actually one of the big reasons why, instead of one big table with 4 quadrants, with a fixture in each quadrant, that's why we went to 6 small tables, was because now instead of slot to slot and quadrant to quadrant, you only have slot to slot, and then table to table, but the table design is going to be much more uniform than a Typhoon table to table. So we did remove the quadrant to quadrant variability there. So that was one step definitely in the right direction. And then the table itself, we did more testing than we've ever done before to help get it as uniform as possible. And that was like what I was talking about yesterday with the different table design iterations that we went through, and I ended up with the floating hammer mount, which helps uniformity. So those are all the kinds of steps that we took to try to make it as easy as we can. So, and I think we definitely took a step in the right direction.
I can make a comment here. Even if you have the uniform table on the uniform RS table as they requested, every time you put the power supply on, the power supply screws force, or how you assemble, one tiny difference will affect the PSD. So trust me, I have seen that before. So I think the what customer request now is just simply because they want everything simple enough for operator to turn on a chamber and turn off the chamber and finish the test, but it's not going to happen.
It'll be a lot closer with Q-Fusion.
Yeah, but it's not happening right now.
No.
There are many discussions about the uniformity of table. So, like when the branding tool need to go qualify the name, we need to give them a spec, right? That spec will be our mass margin for table or something else.
Yeah, the spec will be based. So in Typhoon we have a triangle plate test, TP. So for Q-Fusion it will be a similar test, but instead of a triangle plate going quadrant to quadrant, it's a square plate that goes across the table like slots. So there will be the spec there, GRMS.